Hello my dear student, welcome to video number 140 of my channel MALACHEMPHILIC, and this video number 140 is the 79th episode of Chemical Thermodynamics course, and the topic is Thermochemistry 5th part. So let's see what is there in 5th part or part 5. Already I have shown you this content of thermochemistry, and here you have seen that enthalpy of reaction, enthalpy of formation, enthalpy of combustion, enthalpy of transition, enthalpy of phase change, enthalpy of neutralization already I have finished in my earlier videos. Today I am going to discuss enthalpy of hydration and enthalpy of solution. So let's see. Now, enthalpy of hydration. Look at here. This is copper sulfate solid and it is getting attached, or it gets attached with 5 water molecules, a required number of water molecules, and form the hydrated copper sulfate, and here energy is released. And this energy is known as the hydration enthalpy. So what will be the definition? Definition will be the energy released when 1 mole of the substance combines with the required number of water molecules to form the hydrated substance. So, heat released when 1 mole of the anhydrous compound combines with requisite amount of water molecules to form the hydrate. Now, this hydration enthalpy, that is energy released when 1 mole of the substance combines with water molecules and form the hydrate. This is one definition, but this hydration enthalpy we can apply it for another situation. What is that? See here, gaseous sodium ion combines with water molecules or getting surrounded or attached with water molecules form the aqueous sodium ion. Here also energy released during this hydration, during this attachment of these water molecules, that is known as the hydration enthalpy. So what will be the definition here? Here it will be the amount of energy released when 1 mole of the gaseous ion gets hydrated or dissolved in water and to form the hydrated ions. Okay. Now coming to the factors influencing this hydration enthalpy. First one is ionic radius. Look at here, this hydration enthalpy, already you know what is the definition of hydration enthalpy. Lithium ion is greater than sodium, greater than potassium. Lithium, sodium, potassium, they are in the same group, group 1. Okay, and lithium to sodium, that is they are going top to bottom. So when you are coming from top to bottom in this group, then what is happening? Hydration enthalpy decreases. That means hydration enthalpy is maximum for the ions which is at the top. Okay, then why? Because here when the radius increases, then what will happen? Charge density decreases, or in other words, when radius is less, decreases, charge density increases. So charge density increases means then it will form, that ion can form stronger interaction with the water molecules. So more amount of energy released during hydration. So hydration energy is more for the ion which has less ionic radius. Okay. So hydration energy decreases along the group as the size of the ion increases. Now coming to the ionic charge. Look at here. Aluminium plus 3 greater than magnesium plus 2 greater than sodium. Aluminium, magnesium, sodium, they are in the same period. Okay. Sodium first, then magnesium second group, then aluminium in the third group. Okay. Now, as you are going from left to right in the same period, that is sodium, then magnesium, then aluminium, what is happening? Number one, this radius is decreasing and charge is increasing. So, overall charge density increases. So, when overall charge density increases, then what will happen? Then that the stronger ion dipole interaction, that means ion with the dipole of the water molecules, that interaction increases. So hydration energy or hydration increases. That means that energy released during hydration increases. So here aluminium will have highest hydration energy, then magnesium, then sodium. So hydration enthalpy increases along the period as radius decreases and charge increases. Now coming to the charge size ratio. Same thing. Charge size ratio means charge divided by size. So if the charge increases, size decreases, then charge density increases. Charge density increases means it will attract this water molecule more strongly. That means it will be heavily hydrated. The ion will be heavily hydrated. Thereby, the mobility of the ion decreases. Now coming to the enthalpy of solution. So what will be the enthalpy of solution? Here, heat involved when 1 mole of the substance is dissolved in large excess of solvent at a particular temperature, so that further addition of the solvent does not produce any more heat energy. Okay. So already you have to dissolve in larger excess of solvent. So further if you add the solvent, no more heat energy will be involved. Okay. See, sodium chloride, if you dissolve in water, it dissolves endothermically. That means energy is absorbed. When solid sodium chloride is dissolved, aqueous sodium chloride is formed, then delta H enthalpy of solution is positive. You might have seen that sodium chloride, when you dissolve, the solution becomes cold. Now coming to the enthalpy of the solution of copper sulfate. Look at here. For anhydrous copper sulfate, this enthalpy of solution, that means when you are dissolving in water, this amount of the energy involved, that is minus 66 kilojoules per mole. That means exothermic. So energy is released. But when you are taking hydrated copper sulfate, that is copper sulfate 5H2O, then you see enthalpy of the solution, that means energy involved during solution preparation, that is equal to between 11 to 17 kilojoules. That is positive. That means energy or heat is absorbed. Why? When you are taking anhydrous copper sulfate and dissolving in water, it is getting hydrated. That means the interaction is developed between the ions and the water molecules. So energy is released. Okay, that is exothermic. But when you are taking hydrated copper sulfate, already water molecules are there in the crystal lattice. So first you have to break that attraction, break that interaction between the water and the ions. For that, energy is required. Then during solution preparation, energy will be released. But here, more energy is required to break that interaction. So overall, the energy or enthalpy of the solution is positive. That means heat energy is absorbed. Now coming to one problem. Okay, what is the problem? Enthalpy of solution of this hydrated barium chloride is plus 88 kilojoule per mole. And for anhydrous barium chloride, it is minus 20.6 kilojoule per mole. Calculate the heat of hydration of barium chloride. Okay, this is the problem. Now you see, for 1 minute, just 1 minute. For anhydrous barium chloride, anhydrous barium chloride means this barium chloride solid, and it is dissolving in water, forming this barium chloride aqueous solution. And here this enthalpy of the solution, they have given it as delta H is equal to minus 20.6 kilojoules per mole. See, this is my equation number 1. Okay. Now, for hydrated barium chloride, for hydrated barium chloride, then what is that? So, hydrated barium chloride means this barium chloride and 2 molecules of water of crystallization, that is dissolved and forming this aqueous barium chloride, and you have to break this interaction between the water of crystallization and the ions. So, plus 2 molecules of liquid water, and here delta H, this delta H, here it is for, I am writing anhydrous, this is for hydrated, and this is equal to how much? 88 kilojoules per mole, and this is my equation number 2. Okay. Now, what is the equation for hydration of barium chloride? See, equation for hydration. Equation for hydration of barium chloride, what will be that equation? That is barium chloride solid, okay, plus 2 water molecules, okay, and that is forming the hydrated barium chloride, that is barium chloride twice H2O, and this is solid. This is equation number 3. This is the required equation. How can I get equation number 3? See, equation 1 minus 2, look at here, is equal to equation 3. Look at here, equation 1 is this one, minus 2. If you minus it, this and this get cancelled, right? So, barium chloride minus hydrated barium chloride. Another side, this minus water. So, barium chloride, water, that will give you the hydrated barium chloride. So, delta H, that is enthalpy of hydration, delta H hydration, 1 minute. Delta H hydration, that will be is equal to delta H solution for anhydrous minus delta H solution for hydrated. Okay. So, this is equal to, for anhydrous it is minus 20.6. Okay. Then for hydrated it is plus 88. So, minus of 88. So, it will become 108.6 kilojoules per mole. Kilojoules per mole. So, this is the answer. Now, coming to the next problem. Okay. What is the problem? What is problem number 2? Look at here. 10 gram of urea is dissolved in 150 milliliter of water. the temperature drops from 20.4 degrees centigrade to 16.7 degrees centigrade. Calculate the molar enthalpy of solution for urea. What is given? Heat capacity of water, that is 4.184 joules per gram per degree centigrade, and molecular weight of urea, that is 60 grams per mole. This is the problem. Now, look at here. How to solve this one? See, what is the mass of the solution? See, mass of the solution, that is equal to 150 milliliter water means 150 gram, because water density you know 1 gram per cc, plus 10, that is urea, that is 160 gram. Right? Now, temperature change is how much? Temperature change, that is equal to final minus initial. If I write 16.7 minus 20.4, that means it is minus 3.7 degree centigrade. Right? Now, what is the heat involved during this solution preparation? So, Q solution, that will be is equal to, see, mass, M, mass means M I am writing, into the heat capacity of water, okay, into this change in temperature, right? Heat capacity means heat required for 1 gram of, here per gram it is given, 1 gram of the substance to change the temperature by 1 degree centigrade. So this is for 1 gram. So for m gram, that means 160 gram, that is how much? And for 1 degree centigrade, so delta T, how much degree centigrade is changed. So what is the mass? 160 into heat capacity is 4.184 into this. I am considering only the change of how much temperature change, that is 3.7, and this value is coming 2477 joules. 2477 joules. Okay. Here you see temperature is dropped. That means it is endothermic. Okay. Endothermic. Heat is absorbed. Right. So, and that's why here I have taken only the temperature change. How much is the temperature change? Right. Yeah. Now, number of moles of urea. What is the number of moles of urea? Number of, because you have to find out the molar enthalpy of the solution. Okay. That means molar heat change per mole. Number of moles, 1 minute. Number of moles of urea, that is equal to 10 gram urea you have taken and molecular weight is 60. So it is coming as 0.1667. This is number of moles of urea. Right? So molar enthalpy of the solution will be, so molar enthalpy of the solution, how much it will be? Total heat involved, okay, total heat involved or total enthalpy, that is 2477. Now you have to divide by molecular weight. That means what is the, number of moles. So 0.1667. Okay. So it will give you the molar enthalpy of the solution. So therefore it is coming as 14860 14860 joules per mole. So here you can write, if you take it into kilojoules, you can write 14.860 kilojoules per mole. So this is the answer. Hope it is clear. Thank you.